December 10, 1944. A casualty clearing station, Bastogne, Belgium. The medic's hands trembled as he unwrapped the field dressing from the wounded paratrooper's leg. Steam rose from the infected wound in the frozen air of the makeshift aid station. Sergeant Robert Hayes had seen gangrene before. The telltale smell, the discolored flesh that meant amputation or death. But today, something was different. He reached for a small glass vial from his medical kit, barely larger than his thumb. The label read Penicillin G, 100,000 units. Hayes had never heard of it. Neither had most combat medics. The clear liquid inside looked unremarkable, almost like water. But headquarters had issued specific orders. Inject this into infected wounds regardless of how hopeless they appeared. Hayes prepared the syringe with practiced efficiency, though doubt gnawed at him. How could something produced in what looked like ordinary milk bottles back in some American factory possibly save lives that sulfa drugs couldn't? The wounded soldier winced as the needle found muscle. Within hours, the infection would begin to retreat. What Hayes didn't know was that he was administering the most revolutionary medicine in human history. A drug that transformed the mathematics of battlefield survival and would render obsolete every assumption about wartime mortality the world had ever known. The journey from Alexander Fleming's accidental discovery to the vial in Hayes's hands had taken 15 years. But the final transformation from laboratory curiosity to mass-produced miracle drug had happened in just 18 months, thanks to an unlikely partnership between American ingenuity and repurposed milk bottles. Chapter 1. The Mold That Changed Everything. September 3, 1928. St. Mary's Hospital, London. Alexander Fleming climbed the narrow staircase to his second-floor laboratory after returning from a 2-week holiday in Scotland. The Scottish bacteriologist had left his workspace in characteristic disarray. Petri dishes stacked haphazardly on the bench, bacterial cultures growing in various stages of completion. Fleming had spent years studying Staphylococcus, the bacteria responsible for boils, sore throats, abscesses, and blood poisoning that filled hospital wards across Britain. His colleague Dr. Merlin Price had stopped by to visit, and together they began sorting through the dishes Fleming had abandoned before his vacation. One culture plate caught Fleming's attention. The dish was dotted with colonies of Staphylococcus bacteria, pale yellow clusters that should have covered the entire surface. But near the edge, a blob of blue-green mold had contaminated the plate. That alone was unremarkable. Contamination happened constantly in laboratories with open windows. What stopped Fleming mid-examination was the clear zone surrounding the mold. Where the bacterial colonies should have been thickest, there was nothing. The agar gel had dissolved, as if something secreted by the mold had killed every Staphylococcus bacterium within reach. Fleming isolated the mold and identified it as a rare strain of Penicillium notatum, a common bread mold. He prepared what he called mold juice and began systematic testing against the deadliest bacteria known to medicine. Streptococcus, which caused scarlet fever, meningococcus, responsible for meningitis, the diphtheria bacillus, pneumococcus. Every gram-positive pathogen he tested died on contact with the mysterious substance. Fleming named it penicillin after the fungus genus that produced it. For months, he and his assistants, Stuart Craddock and Frederick Ridley, attempted to isolate pure penicillin from the mold juice. The substance proved maddeningly unstable, breaking down within days even when refrigerated. They managed only crude preparations that lost potency within hours. Fleming published his findings in the British Journal of Experimental Pathology in June 1929, noting penicillin's remarkable antibacterial properties. But his report included only a passing reference to therapeutic applications. The medical community barely noticed. When Fleming presented his work to the Medical Research Club, his colleagues showed polite disinterest. Professor Harold Raystrick, one of Britain's leading biochemists and an expert in fungal substances, attempted to purify penicillin at Fleming's request. After months of failure, Raystrick declared the production of penicillin for medical use almost impossible. The substance was too unstable, too difficult to isolate, too impractical for clinical application. Fleming agreed. By 1930, he had relegated penicillin to a laboratory curiosity, useful only for isolating certain bacteria in mixed cultures. The mold juice that could kill humanity's deadliest pathogens was filed away, forgotten in the basement archives of St. Mary's Hospital. Fleming returned to other research. The petri dish that had changed everything gathered dust. Outside the laboratory windows, the world moved toward another war, one that would fill hospitals with infected wounds, septic amputations, and deaths from bacterial infections that penicillin could have prevented. But in 1939, two scientists at Oxford University would discover Fleming's abandoned research and recognize what he had missed. Chapter 2: Oxford's Desperate Gamble. January 1939, the Sir William Dunn School of Pathology, Oxford University. Howard Walter Florey sat in his office reviewing research proposals as Europe teetered on the edge of war. The Australian-born pathologist had recently been appointed to lead Oxford's pathology department, and he understood what another continental conflict would mean. The Great War had killed more soldiers from infected wounds than from bullets. Florey had watched men die from gas gangrene, from blood poisoning that turned limbs black, from pneumonia that filled lungs with fluid until they drowned. Sulfa drugs offered limited protection, but they failed against many bacterial infections and caused dangerous side effects. Florey assigned biochemist Ernst Boris Chain to survey the scientific literature on naturally occurring antibacterial substances. Chain, a Jewish refugee who had fled Nazi Germany in 1933, began cataloging forgotten research papers. In a dusty Oxford library, he discovered Fleming's 1929 publication describing penicillin. The paper intrigued him. Fleming had demonstrated that this mold substance killed Staphylococcus, Streptococcus, and other deadly bacteria. Yet no one had pursued it. Chain brought the paper to Florey in early 1939. By September, Britain was at war. Florey assembled a team that included Chain, biochemist Norman Heatley, and research assistant Margaret Jennings. They began with virtually nothing: no funding, no facilities designed for mold cultivation, no established methods. Heatley improvised extraction equipment from bedpans, tin cans, and milk churns. Chain developed a freeze-drying technique that stabilized crude penicillin long enough to test it. On May 25, 1940, as German panzers drove toward the English Channel and Britain faced potential invasion, Florey conducted the experiment that would change medicine. He injected 8 white mice with lethal doses of Streptococcus bacteria. 4 received penicillin injections. 4 received nothing. By the next morning, all 4 untreated mice were dead. All 4 treated mice were alive and showed no signs of infection. Florey repeated the experiment with identical results. The Oxford team now possessed proof that penicillin could cure systemic bacterial infection in living organisms. By February 1941, they had accumulated enough penicillin to attempt the first human trial. A 43-year-old Oxford policeman named Albert Alexander lay dying from a mixed bacterial infection that had started with a scratch from a rose thorn. The infection had spread to his eyes, scalp, and lungs. Florey administered intravenous penicillin. Within 24 hours, Alexander's fever had dropped, and his condition improved dramatically. But after 5 days, the penicillin supply was exhausted. The team had even extracted and repurified penicillin from Alexander's urine to extend treatment. It was not enough. Without continued doses, the infection returned. Alexander died on March 15, 1941. The trial proved penicillin's effectiveness but revealed a crushing reality. Britain lacked the industrial capacity to produce it at scale. Every pharmaceutical facility in the country was manufacturing explosives, ammunition, or essential war materials. The British government could not divert resources to construct fermentation plants for an unproven medicine. Florey made a decision that would determine the outcome of the war. On June 27, 1941, he and Norman Heatley boarded a Pan American Airways flying boat bound for New York. They carried the penicillium mold strain in their coat pockets, having rubbed spores into the fabric in case German U-boats torpedoed their aircraft. If they died, perhaps someone would find the mold and continue the work. Within weeks, they had convinced the U.S. Department of Agriculture's Northern Regional Research Laboratory in Peoria, Illinois, to join the effort. American researchers led by Robert Coghill and Andrew Moyer began testing thousands of mold strains and growth mediums. In November 1941, laboratory technician Mary Hunt brought in a moldy cantaloupe from a Peoria market. The mold growing on its rind was Penicillium chrysogenum, and it produced 200 times more penicillin than Fleming's original strain. When Moyer tested corn steep liquor, a waste product from Midwestern corn processing, as a growth medium, yields increased by another 500 times. American pharmaceutical companies Merck, Squibb, Pfizer, and Lederle committed to the project. But one problem remained unsolved. Even with the improved strain and growth medium, existing surface culture methods could never produce enough penicillin for a European invasion. The race to solve mass production had just begun, and D-Day was less than 3 years away. Chapter 3. Milk Bottles and Bedpans. The laboratories looked more like improvised kitchens than pharmaceutical facilities. Rows of sterilized milk bottles lined wooden shelves in temperature-controlled rooms across Britain and America, each pint bottle filled with golden brown nutrient broth. Glass bedpans, ceramic hospital containers, food tins, anything that could be sterilized and sealed became a vessel for growing penicillium mold. The surface culture method required shallow containers where the mold could spread across the liquid surface, forming a thin film that slowly secreted penicillin into the broth below. At the Allen and Hanbury's factory in Ware, Hertfordshire, newly qualified pharmacists worked in pilot plants that operated around the clock. They sterilized milk bottles in autoclaves, filled them with precise amounts of nutrient medium, then moved them to aseptic rooms where technicians inoculated each bottle with penicillium spores. The bottles then spent 7 to 10 days in incubator rooms held at exactly 22 degrees Celsius. After fermentation, workers extracted the penicillin-laden liquid, filtered out the mold, and began the painstaking purification process. Each bottle yielded only tiny amounts of usable penicillin, perhaps enough to treat one infected wound for a single day. American facilities operated under the same constraints. By early 1942, the combined output of all U.S. pharmaceutical companies producing penicillin could treat fewer than 100 patients. The War Production Board tracked every gram. Military planners calculated that an invasion of Europe would require treating tens of thousands of infected wounds simultaneously. At current production rates, they would never accumulate sufficient supply. Ann Miller changed that calculation. The 33-year-old Connecticut woman lay dying at New Haven Hospital in March 1942. A miscarriage had triggered streptococcal septicemia, blood poisoning that spread through her entire system. Her temperature spiked above 106 degrees Fahrenheit. Sulfa drugs had failed. Her doctors estimated she had days, perhaps hours, to live. Dr. John Bumstead contacted officials who controlled America's penicillin reserves and requested an emergency allocation. On March 14, 1942, they delivered half of the entire United States penicillin supply to New Haven Hospital. The amount would barely fill a small vial. Bumstead administered the first injection at 3:30 that afternoon. By evening, Miller's temperature had dropped to 100 degrees. By the next morning, she was sitting up and eating breakfast. The infection had vanished. Ann Miller survived to live another 57 years. The successful treatment validated everything Florey's Oxford team had discovered. Penicillin worked in humans. It could cure infections that sulfa drugs could not touch. News spread through the medical community and reached military commanders planning the eventual return to Europe. Demand exploded. But the supply crisis deepened. Miller's treatment had consumed half of America's penicillin reserves. Producing more required exponentially more containers, more laboratory space, more skilled technicians, and more time than the invasion planners could afford. In Brooklyn, New York, Pfizer engineer Jasper Kane examined the problem from a different angle. His company had spent decades perfecting deep tank fermentation for producing citric acid. Kane understood that surface culture methods would never scale to military requirements. Growing penicillin in shallow containers was inherently limited. Each bottle could only hold so much liquid, and the mold only grew where it contacted air at the surface. Kane proposed adapting deep tank fermentation technology to penicillin production. Instead of growing mold in thousands of shallow bottles, they could use massive aerated tanks where the mold would grow throughout the entire volume of liquid, not just at the surface. The concept borrowed from brewing beer, forcing air through submerged cultures to provide oxygen while the mold multiplied in 3 dimensions rather than 2. The risk was enormous. Deep tank fermentation had never been attempted with penicillium. If contamination occurred in a milk bottle, workers discarded 1 pint of culture. If contamination occurred in a 7,000-gallon tank, the entire batch would be lost. but Kane believed the method could increase production by factors of 100 or more. Word of Pfizer's proposal reached the War Production Board as 1942 drew to a close. Allied forces were fighting in North Africa. Soviet armies battled for Stalingrad. And somewhere in the planning rooms of Washington and London, staff officers were calculating how many soldiers would die from infected wounds when the invasion of France finally came. Chapter 4. Deep Tank Revolution. Pfizer's facility at 81 Flushing Avenue in Brooklyn occupied a former ice manufacturing plant. The old brick building still housed the massive refrigeration machinery required for temperature-controlled industrial processes. In early 1943, Jasper Kane walked through these cavernous spaces with engineers who thought his proposal bordered on madness. Converting ice-making equipment into sterile fermentation tanks, capable of growing billions of microscopic organisms, represented engineering challenges that had never been solved at this scale. Kane had built his reputation perfecting deep tank fermentation for citric acid production during the 1920s. The process involved cultivating microorganisms in massive aerated tanks rather than shallow dishes. Compressed air forced through perforated pipes at the tank bottom provided oxygen while mechanical agitators kept the culture in constant motion. For citric acid, contamination meant losing money. For penicillin, contamination could mean losing the war. The first experimental tank held 7,000 gallons of corn-steeped liquor nutrient medium. Workers welded stainless steel panels into a cylinder 14 feet high, then installed heating coils to maintain precise temperature. Air compressors capable of forcing sterile, filtered air through thousands of gallons of liquid were positioned outside. Inside, paddle agitators driven by electric motors would keep the penicillium mold suspended throughout the medium rather than floating on the surface. On March 1, 1944, the world's first pharmaceutical-scale deep tank fermentation facility opened for production. Within days, it became clear that Kane's gamble had worked. A single 7,000-gallon tank produced as much penicillin in one fermentation cycle as 10,000 milk bottles using surface culture methods. The mold grew throughout the entire volume of liquid, multiplying production capacity by factors that had seemed impossible just months earlier. Other pharmaceutical companies watched Pfizer's results and accelerated their own deep tank programs. Merck constructed facilities in Rahway, New Jersey. Squibb built tanks in New Brunswick. Abbott Laboratories, Commercial Solvents, Park Davis, Upjohn. 21 companies in total received War Production Board authorization to construct penicillin facilities. The government designated these plants as essential war industries, giving them priority access to steel, copper piping, and construction materials that were otherwise reserved for weapons manufacturing. Production numbers told the story of American industrial mobilization. In 1943, U.S. facilities produced 21 billion units of penicillin. By 1944, that figure had climbed to 163 billion units, an increase of nearly 8,000%. By June 1945, monthly production exceeded 646 billion units. The price collapsed from $20 per treatment dose in July 1943 to 0.55 by 1946. What had been more precious than gold became affordable enough for routine medical use. The War Production Board coordinated the entire effort with the singular objective of ensuring adequate penicillin supply for the invasion of Europe. Chemical engineer Margaret Hutchinson Rousseau designed the production plants that would make this possible. Her work translating laboratory procedures into industrial-scale processes solved contamination problems that had plagued earlier attempts. Every tank, every pipe connection, every valve had to be sterilized and maintained under aseptic conditions throughout the fermentation cycle. A single airborne bacterium entering a 7,000-gallon tank could destroy the entire batch. By May 1944, American pharmaceutical companies had stockpiled 2.3 million doses, enough to support the Allied invasion force landing at Normandy. Combat medics would carry penicillin in their field kits for the first time in military history. The drug that 10 years earlier had been dismissed as a laboratory curiosity was now being mass-produced in quantities sufficient to treat entire armies. But across the Atlantic, German pharmaceutical scientists faced a different reality. Nazi Germany's synthetic fuel program consumed resources that might have gone to antibiotic research. Their attempts to replicate Allied penicillin production would fail, leaving Wehrmacht soldiers to face infections with only sulfa drugs, the same inadequate treatment that Allied forces had abandoned years earlier. The Industrial Revolution and penicillin production had created a medical asymmetry that would prove as decisive as any weapon deployed in the European theater. Chapter 5. Germany's Failed Race. German military doctors first encountered penicillin on the battlefields of North Africa in 1943. Allied medics carried vials of the clear liquid in their field kits, administering it to wounded soldiers whose infected wounds healed with unprecedented speed. Wehrmacht physicians recovered these vials from captured Allied medical supplies and sent them to pharmaceutical laboratories in Berlin for analysis. The reports confirmed what battlefield observations had suggested. The Allies possessed an antibiotic far superior to anything Germany had developed. The German chemical industry had pioneered synthetic drug manufacturing during the interwar period, producing sulfa drugs that had saved thousands of lives. But penicillin was different. It could not be synthesized chemically. It required cultivating living organisms under precise conditions, then extracting and purifying the antibacterial compound they produced. By the time German scientists understood this, Allied production facilities were already operating at industrial scale. In occupied Holland, scientists at the Nederlandse Gist en Spiritusfabriek, yeast and alcohol factory in Delft, received orders to develop domestic penicillin production. The facility operated under German military oversight, with guards stationed to monitor the Dutch workers. The scientists faced an impossible challenge: replicate years of Allied research and development while working under Nazi occupation with limited resources and constant surveillance. They began with the same primitive methods that Oxford had used 4 years earlier. Sterilized milk bottles lined laboratory shelves, each filled with nutrient broth and inoculated with penicillium spores. The scientists called their product Bastogne, partly to disguise its true nature from their German overseers. The work proceeded in secret, with researchers sharing information only among trusted colleagues. They faced a particular problem in the form of a German guard assigned to monitor their activities and ensure nothing subversive occurred in the laboratory. The solution proved remarkably simple. The guard knew nothing about microbiology and had a weakness for gin. The Dutch scientists kept him perpetually drunk. As one researcher later recalled, they made sure he got plenty of alcohol, and he spent most afternoons asleep. Under this arrangement, production of Bastogne continued from July 1944 through March 1945. By October 1944, the NG&SF team had successfully produced penicillin. They grew the mold in hundreds of milk bottles using surface culture fermentation, the same tedious process that Allied scientists had abandoned 2 years earlier in favor of deep tank methods. The Dutch facility could produce enough Bastogne to treat a few dozen patients, perhaps a few hundred if supplies were stretched. But Wehrmacht casualties numbered in the hundreds of thousands. Even if every pharmaceutical facility in occupied Europe had replicated the NG&SF process, Germany could never match Allied production capacity. The industrial infrastructure required for mass production simply did not exist. Deep tank fermentation required specialized facilities, massive steel tanks, air compression systems, and uninterrupted power supplies. Allied strategic bombing had systematically destroyed German chemical plants throughout 1944. The synthetic fuel program consumed what remained of Germany's pharmaceutical manufacturing capacity. Penicillin production at scale would have required diverting resources from weapons, ammunition, and fuel production, priorities that Hitler's regime would never sacrifice for medical supplies. German soldiers continued receiving treatment with sulfa drugs and antiseptics that had been standard medical practice in 1918. Field hospitals in France, Italy, and the Eastern Front reported infection mortality rates that Allied forces had not experienced since the previous war. Wehrmacht physicians watched their patients die from gas gangrene, blood poisoning, and pneumonia, while knowing that Allied medics possessed medicine that could save them. The NG&SF scientists did not even know for certain that Bastogne was chemically identical to penicillin until after the war ended. In 1945, they obtained samples of British penicillin and compared them to their own product. The compounds matched. What they had produced in secret under German occupation in milk bottles hidden in a Dutch factory was indeed penicillin. They began commercial marketing in January 1946. But for the German military, success came too late and in quantities too small to matter. The medical asymmetry created by Allied antibiotic production had become another invisible factor grinding down Wehrmacht combat effectiveness. Soldiers who survived bullets still died from infections. The wonder drug existed, but only on one side of the front lines. Chapter 6. The D-Day Difference. Allied Supreme Commanders planning Operation Overlord understood the mathematics of amphibious assault. Historical data from Gallipoli, Dieppe, and the Pacific Island campaigns provided grim projections. Thousands of men would be wounded in the first hours. Those who survived the initial assault would face the oldest enemy of warfare: bacterial infection from contaminated wounds, unsanitary field conditions, and the inevitable sepsis that turned minor injuries into death sentences. General Dwight Eisenhower's medical staff calculated that based on World War I infection rates, 15 to 20% of wounded soldiers would die not from their wounds, but from subsequent bacterial infections. Gas gangrene caused by Clostridium bacteria in soil had killed thousands in the trenches of France between 1914 and 1918. Blood poisoning from streptococcus turned scratches into systemic infections. Pneumonia filled the lungs of men weakened by trauma and shock. In the previous war, these infections had been uncontrollable. But on the morning of June 6, 1944, every combat medic waiting ashore at Omaha, Utah, Gold, Juno, and Sword beaches carried something their predecessors never had. Tucked into their field medical kits, alongside morphine syrettes and sulfa powder, were small glass vials labeled Penicillin G, 100,000 units. American pharmaceutical companies had produced 2.3 million doses specifically for the Normandy invasion. The instructions were simple and revolutionary. Inject wounded soldiers immediately after triage, before infection could establish itself. The transformation in battlefield medicine occurred within hours. Medics treated soldiers hit by shrapnel, bullets, and fragmentation with immediate penicillin injections. Men with compound fractures, abdominal wounds, and traumatic amputations received doses every 3 to 4 hours throughout evacuation and surgery. Field hospitals that in previous wars would have filled with gangrene cases instead processed patients whose wounds remained clean and began healing within days. Statistical analysis conducted after the Normandy campaign revealed numbers that military medical officers could barely comprehend. Infection mortality had dropped by more than 80% compared to World War I rates. Soldiers who would have died from gas gangrene in 1918 survived to return to their units in 1944. The average hospital stay for infected wounds had decreased from weeks to days. Remarkably, the return-to-duty rate for wounded personnel had increased dramatically. Men who received immediate penicillin treatment could rejoin combat operations in timeframes that would have been impossible with sulfa drugs alone. The invisible strategic advantage compounded throughout the campaign. Every soldier saved from infection mortality represented preserved combat strength. Every week shaved off hospital recovery time meant another rifle back on the front line. American and British forces could sustain offensive operations because their wounded were surviving and recovering at rates no military in history had achieved. German physicians captured after the Normandy campaign expressed disbelief when they toured Allied field hospitals and observed penicillin administration protocols. One Wehrmacht surgeon later recalled being stunned, not by Allied tactical superiority, but by their medical capabilities. He watched American medics inject penicillin into wounded German prisoners with the same routine efficiency they used for their own casualties. The German doctor had never seen antibiotics administered at such scale. His own field hospital relied on sulfa drugs, antiseptics, and surgical debridement, techniques that were already obsolete. When shown the American pharmaceutical production facilities after Germany's surrender, captured German scientists could not comprehend how the Allies had industrialized a living organism. The deep tank fermentation plants, the quality control laboratories, the logistics networks distributing millions of doses across multiple theaters, it represented an achievement in biotechnology that Germany's war economy had never attempted. One German chemist examining Pfizer's Brooklyn facility remarked that this alone might have changed the outcome of the war. The medical asymmetry had indeed become a strategic weapon. While Wehrmacht soldiers continued dying from infected wounds at rates comparable to the previous war, Allied forces had fundamentally altered the relationship between combat trauma and bacterial infection. Penicillin had not prevented wounds, but it had severed the connection between wounding and death from infection. By the time Allied armies reached the Rhine in 1945, combat medics had administered penicillin to hundreds of thousands of wounded soldiers. The drug that had been dismissed as impractical in 1930, that existed in quantities measured in drops in 1942, now flowed through military medical supply chains as routinely as ammunition moved to the front lines. The vials that Sergeant Hayes had administered in Bastogne represented the final stage of a medical revolution that began with Fleming's contaminated petri dish and culminated in the deep tank fermentation plants of Brooklyn. But the revolution was not finished. Chapter 7. From Milk Bottles to Miracles. The War Production Board released penicillin for commercial distribution to American civilians on March 15, 1945. For the first time since Fleming's discovery 17 years earlier, the drug that had saved hundreds of thousands of military lives became available to the public. Pharmacies across the United States stocked the medicine that parents had read about in newspapers, that they knew had saved soldiers overseas, and that could now save their own children from scarlet fever, pneumonia, and blood poisoning. By January 1945, American pharmaceutical companies were producing 4 million sterile packages of penicillin per month. The production capacity that had been built to supply D-Day now turned toward civilian medicine. Doctors who had treated bacterial infections with sulfa drugs and antiseptics suddenly possessed an antibiotic that worked against pathogens their previous medicines could not touch. Children who would have died from streptococcal meningitis survived. Women who contracted post-surgical infections recovered within days. The pneumonia that had killed thousands annually became a treatable condition. The transformation occurred so rapidly that many people failed to grasp its significance. In 1930, penicillin had been dismissed as impractical. In 1942, half of America's entire supply had been required to save one woman's life. By 1946, penicillin cost 55 cents per dose, and pharmacies carried it as routinely as aspirin. The price had collapsed by a factor of nearly 40 in just 3 years. Fleming, Florey, and Chain received the Nobel Prize in Physiology or Medicine in 1945 for their roles in penicillin's discovery and development. But the true miracle had occurred in the factories of Brooklyn, Rahway, and New Brunswick, in the deep tank fermentation plants where American engineers had solved the problem of mass production. Chemical engineer Margaret Hutchinson Rousseau, who designed many of those production facilities, never received comparable recognition. Her work translating laboratory procedures into industrial-scale processes had been as essential to penicillin's success as Fleming's contaminated petri dish. The story that began with milk bottles filled with golden brown broth had ended with industrial facilities producing billions of units monthly. The improvised containers that British and American researchers had used in 1941, the bedpans, the food tins, the sterilized glass bottles borrowed from dairies, had become symbols of resourcefulness during the war's darkest period. They represented what was possible when scientific discovery met industrial determination and government coordination. Sergeant Robert Hayes returned home to Ohio in 1946. He never learned the complete story of the vials he had carried in his medical kit at Bastogne. He did not know about Fleming's vacation in 1928, or Florey's desperate mission to America in 1941, or the Peoria laboratory technician who found a moldy cantaloupe that increased penicillin yields by 200 times. He did not know about Jasper Kane's gamble on deep tank fermentation, or the German scientists in occupied Holland keeping their guard drunk while they secretly produced Bastogne in milk bottles. But Hayes understood what mattered. The clear liquid in those small vials had saved lives that sulfa drugs could not. The infected wounds that would have meant amputation or death in previous wars had healed cleanly. Soldiers who should have died walked off transport ships and returned to their families. The mathematics of warfare had fundamentally changed. In World War I, 12 to 15% of wounded soldiers treated in frontline hospitals died from infections, most notably from gas gangrene. In World War II, that mortality rate dropped to 3%. The difference was penicillin. Not tactics, not weapons technology, not strategic brilliance. A medicine grown from mold and produced in tanks that once made ice. The medical revolution launched by penicillin continued long after the war ended. Streptomycin followed in 1944, effective against tuberculosis. Tetracycline emerged in 1948. The antibiotic age had begun. transforming human life expectancy more dramatically than any medical advance in history. By the 1950s, diseases that had killed millions for centuries became treatable conditions. But the story also carried a warning that military medical officers recognized even in 1945. Bacteria would adapt. Overuse and misuse of antibiotics would eventually create resistant strains. The miracle drugs that had changed the mathematics of death would one day face diminishing effectiveness. For the men who fought in Europe between 1944 and 1945, those concerns belonged to a distant future. They had witnessed medicine save lives at a scale their father's generation could not have imagined. They carried home the knowledge that science, when mobilized with purpose and urgency, could accomplish the impossible. The vials of penicillin that medics administered on battlefields from Normandy to the Rhine represented more than medicine. They symbolized what humanity could achieve when confronted with its oldest enemy. Not the enemy in uniform, but the microscopic killers that had followed armies throughout history. For the first time, medicine had won. And it all began with milk bottles, a forgotten laboratory paper, and the refusal to accept death as inevitable.